I am happy.
All right. Let's get started. Hey, let's get started. So you guys have, I just don't want to steal your valuable complex analysis time from you. I graded most of I haven't graded quiz 1 yet. I graded most of the quiz 2s. I'm not going to give them back because I'm still waiting on like 3 people taking it. So your scores are up on quiz 2. I should have it back tomorrow. It's like, here's another homework assignment. So the homework assignment covers stuff that, so the 1.3 stuff is largely what we talked about with multi-valued functions and inverses. And then I've got a couple of questions here from 1.4, which is about the Cauchy-Riemann equations, which is what I'm starting today. We'll talk about Cauchy-Riemann equations. I may add more to this, but it seems like this is a reasonable set for right now. And then if I add more, it might be till next week. So let me talk a little bit about the order of topics I'm going to do, because if you look along in the book, there's a couple of sections I'm skipping. So I'm not going to talk about, so later, because I think they're sort of unmotivated right now and I can't really do them justice. Later, I'm going to give a full treatment to Riemann surfaces and analytic continuation. But those ideas link up with ideas from, say, algebraic topology and geometry, and it makes more sense to do them after we've been through the foundations of complex analysis, and then either at the end of this quarter or through next one, I can show you how these ideas lead to some pretty major ideas in algebraic geometry, in complex variables, several complex variables, differential geometry, this number theory that this is the sort of birthplace of a lot of ideas that seem like they would be analysis, but they are. But if I do it now, it's just going to be a quick oh, hey, look, here's a thing a computer drew, and now let's go on. So I encourage you to read these sections if you want to read. So these are the later parts of 1.3, and this is section 1.5. And please don't keep yourself from reading these things. There's good stuff in there. I just can't do it justice right now as part of a lecture, and I don't want to. It's hard enough to keep this stuff with one thread running through it, and I think these are sort of distractions from what I want to do at the moment. Okay, what else did I want to say here? Great. So, kind of where we left off was, what did we do last time? We did multi-valued functions, right? Multi-valued functions and inverses. So we're going to start with a different idea, which is in section 1.4. And the idea that I want to talk about in 1.4 is called the Cauchy-Riemann equations. And what the Cauchy-Riemann equations give you is a way of testing if a function is holomorphic. So right now, what we've got, what does holomorphic mean? Differentiable and that's entire. Differentiable everywhere is entire. Differentiable, somebody over here said differentiable on a disk. That's right, yeah. Differentiable on all the points inside some open disk is what we mean by holomorphic. So basically at the moment what we have is sort of what we already know. Let's see, this marker to the test here. So we know that if a function is analytic, what does analytic mean?
Converges uniformly to power series.
Yeah, it has a power series to which the function uniformly converges on some disk. Yep. So we know that analytic implies holomorphic. So if I knew that a function had a power series, that it converged uniformly on some disk, or absolutely uniformly on some disk, then I would know that the function was holomorphic. But that's an irritating condition to have to check, because we don't have Taylor's formula. So I have no way of generating power series. If I just give you a function, it's basically impossible, impossible to tell if the function is holomorphic. Right? And so what the Cauchy-Riemann equations are going to give us is a way of, this is distracting. Well, it's like it's going to be a video where all you can see is my neck, which is sort of hilarious, but distracting me. So what we'd like to have is some other test. We'd really like a test for, I'm going to use the word holomorphicity. I can define any word I want. I mean, really, what we want to, it is actually, but we want to check to see that like what we're doing is we're trying to check to see if a function is holomorphic without having to guess at some convergent power series. And that's what the Cauchy-Riemann equations are going to give us, is a criteria that we can use to decide whether or not a function is holomorphic. So I'm going to start with a theorem, and then we're going to go back and try to justify why it might be true. And we're going to talk about applications of examples. And one direction of this proof is really easy. And we'll do that direction today, probably. The other direction is like long-winded nightmare of linear approximation. So if I do that direction, next time I'm going to wave my hands at it to give you an idea of the flavor of it. And we're not actually going to do it, and you're not responsible for it. So the forward direction is easy and is related to ideas you've seen before. The backwards direction, if you really want to know, I have a video where I actually did it all. So I'll post that. Okay, so let's suppose that u of x and y and v of x and y are real valued and C1. Okay, what does it mean to be C1? Yep. Not just once differentiable. Continuous first derivatives. Better than once differentiable. It's possible to be once differentiable and have awful derivatives, right? So my favorite family of terrible functions, everybody should have a favorite family of terrible functions. My particular favorite family of terrible functions is the family that looks like this. X to the n sine of 1 over x. And then where you let it be equal to 0 when x is equal to 0. You can make this have whatever order you want, and the next order fails. So this family, by choosing the right power of n, you can force this thing to have any level of regularity you want. Do you want it to be C1 and not C2? Pick the right power of n. So that means the third derivatives don't exist, the second derivatives exist but are not continuous, but every previous derivative is continuous. Like, you can do that by putting x to the third right there, for example.
Hey, can I just ask you to outside really quickly?
Sure.
Thank you.
Not me. Anyway, hold on, I got distracted here. Oh, okay. So these guys. Okay, so this is my favorite family of functions, because you can introduce, like, really, you should really sit down and look at what these things act like, right? These are awful, but hilariously awesome at the same time. Okay, so we're going to start by assuming that functions are C1, and then let's say that on some disk, on a disk centered at z is equal to a, and I guess we can call the disk S. So a disk, I don't know why the book uses S, but a disk S centered at z equals a. That is hard to read what I wrote there, so let me rewrite that. A function is real valued in C1 on a disk S centered at z is equal to a. So even the notation might look confusing. Remember, the way we're thinking about this is we're feeding in complex numbers, x plus iy, and we're thinking of these functions as functions that eat complex numbers but produce real numbers. Okay. So ultimately, these are going to be the real and imaginary parts of a complex function. Then f of z is equal to f of x plus iy, which is equal to u of xy plus iv of xy. Sorry. Somebody's chatting me. Is differentiable, is complex differentiable, right? Really holomorphic, but we'll say differentiable. Differentiable on the disk. Differentiable at every point on S, if and only if. So This is a characterization of holomorphic functions. If and only if ux is equal to vy and minus, let's do it this way, uy is equal to minus vx. And what I mean by this is the partial derivatives. So this is x partial derivative and y partial derivative. So I'll remind you that the symbol ux means the partial derivative with respect to x of u of x and y, and the symbol uy means the partial derivative with respect to y of u, x and y. And this is kind of weird, right? Because this looks, for all the world, like a theorem about real functions. I mean, there's nothing, I mean, why should this even be about complex functions? I just have this collection of differential equations that describe the behavior of real valued functions. And I don't even need to think about them as real valued functions and take complex inputs, because why couldn't I just think of this as a circle in R2? And that's a, yep.
Oh, sorry.
No, please.
But if U and V are like not C1, do you then just know right off the bat that F is not differentiable?
It can't be, yeah, because ux and so the way to think about the way partial derivatives work is they're derivatives in particular directions along particular lines. So if I have a complex function and there's a line on which ux or uy doesn't exist, then that means it can't be holomorphic, because it's not even differentiable at that point, because to be differentiable in more than one variable or in complex variables means differentiable from every possible direction on a disk that comes in. So this is actually really special, because what we're saying is I only have to check two lines. I have this function at C, yeah, so not C1 means automatically it can't possibly be complex differentiable, because complex differentiable is way stronger than C1. But this is saying there's just two directions I need to check. I check two directions for the derivatives of the real and imaginary part of a complex function, and if those two directions happen to be differentiable, then it's differentiable on the entire disk, which is kind of an absurd sounding statement. But again, the way the complex analysis works, you shouldn't be surprised, because it seems like we're getting extra structure everywhere. All right, I gotta, yes?
Can you check in general in any two linearly independent directions?
That is a good question. I think the answer is yes under change of variables, but you wouldn't necessarily do that.
Right, it would be.
Like, but yeah, all you really need is that the linearly independent variables reconstruct the tangent plane, basically. Yep.
Is there a notion of a directional derivative?
In complex analysis, there is, yeah. Because you can always, I mean, so thinking about complex analysis as a vector space, you can always define directions, and then you can like take H in that particular direction. So yeah, we'll actually see some of that when we look at, I mean, every notion from complex analysis maps back to one from the calculus of two real variables. And so there's very much like if it exists in the calculus of two real variables, it comes over. All right, so now I've got a pop quiz. Not really, because I'm not picking it up. But does anybody remember the definition or the theorem? Those of you that had me in previous class don't get to answer this question. What does Clairaut's theorem say?
Mixed order partial. If it's a nice function, mixed order partial derivative is very close.
Ah, okay. So Clairaut's theorem. Nice job. Clairaut's theorem says that if a function is nice, Clairaut's, you guys use this all over Math 241 if you took it here, right? Clairaut's theorem says that if f in x and y is nice, then mixed partial derivatives f, x, y are equal to each other. So that is, taking the x derivative of the y derivative of f is equal to taking the y derivative of the x derivative of f. Right, so I think, what are the conditions on f? Like, it has to be C1. It has to be C1, and the second derivatives have to exist everywhere, right? And then you get this. So there's some of this flavor is going to show up in what we're doing here, right? This is a structural theorem that says that if f is nice, if the derivatives of f are nice enough, then it doesn't matter what order you take the partial derivatives in. In some sense, you can think about what it means as the graph of f, the surface that f produces, can't have any weird bends in it. And that's ultimately kind of what's going on here too. Complex functions have such nice graphs that they produce in some sense that their derivatives are forced to follow this really strong behavior. So first, I'll give you an example of how it works, and then I'm going to give you a taste of how the argument, I'm going to show you how the argument works in the forward direction. If we have a holomorphic function, then the Cauchy-Riemann equations work. And then I may have time to give you a flavor of the other direction, but I'll definitely show you next time if I can't show you this time. So how do these work? So suppose that somebody came along and said, I don't believe you that f of z is equal to z squared is holomorphic. I come along and I claim that that's true. I give you this theorem, and then you say, well, why should that be differentiable everywhere? I don't know the definition of differentiability. What do you mean? How can I say for sure that's holomorphic? So if you want to show something is holomorphic or not holomorphic using the Cauchy-Riemann equations, you actually need to present it in the real part, imaginary part setup. So what we're going to do is we're going to try to find u of x and y and v of x and y. You should recognize this exercise because we did it in the homework already, right? So we're going to say, okay, well, think about f. So first we're going to find the real part of f, which is equal to u, and the imaginary part of f, which is equal to v. And the way we do that is we use the presentation where we think about z as being x plus iy. So f of x plus iy is x plus iy squared, which is x squared minus, what am I doing, plus 2i xy minus y squared. I sort that into its real and imaginary parts. X squared minus y squared plus I times 2xy. And having done that, having sorted the function out into these two pieces, that is the real and imaginary part that I want to work with. I should put this in the center of the board here. So we had f of x plus iy was equal to x plus iy squared, which is x squared minus y squared plus I times 2xy. Okay, so here's the claim. U of xy is equal to x squared minus y squared, and v of xy is equal to 2xy. Notice, real valued functions. There's no i's anywhere, right? We've sorted it entirely into two real valued functions. Are those functions C1?
Yeah.
Why? Because polynomials, and polynomials are nice, right? All derivatives of polynomials exist to all orders, and they're all smooth, right? So, u and v are C1 everywhere. There's no bad spot in those functions, right? When I say C1, I mean all of, if I want to be more pedantic, what I'm arguing here is ux, uy, vx, and vy are continuous everywhere. And if you want to impress your poor, overworked math professor, you could actually calculate these things. Because practicing your partial derivatives, if you haven't taken them since you took 241 2 years ago, if that's how long it's been, ux is 2x. Oh, look, it's a continuous function. Uy is minus y. Oh, look, another continuous. I can't even do it right. Minus 2y, another continuous function. Good thing that's on video, me computing that partial derivative. Vx is 2y, and vy is 2x. Everything continuous, the function is C1. Okay, so we've met the hypotheses of invoking the Cauchy-Riemann theorem. Now I just need to check that these equations are true, which I've fortunately computed the partial derivatives I need in checking that they were continuous. So the question you now ask yourself is the x derivative of u equal to the y derivative of v? Oh, look. X derivative of u and the y derivative of v are the same. So Cauchy-Riemann equation 1 is satisfied. Is the y derivative of u the negative of the x derivative of v? Certainly. So both Cauchy-Riemann equations are satisfied. That is to say, ux is vy and also minus ux is equal to vx, uy is equal to vx. So by the Cauchy-Riemann equations, which you are absolutely allowed just to say CRE because that's what everybody does. So by the Cauchy-Riemann equations, f of z is equal to z squared is holomorphic everywhere. And you can imagine that one of the classic exercises in complex analysis class is to give you some ugly function and force you to prove that that function is holomorphic by grinding out a bunch of, sorting a function into its real and imaginary parts, computing these partial derivatives. Okay, and that's not just like a pedantic exercise. It's something where doing this sort of like deconstruction of functions is at the heart of using complex analysis. Oh, holomorphic, sorry, yeah, that's kind of a mess. Holomorphic everywhere is what that was meant to say. Is holomorphic everywhere. And what I mean by that is, it was C1 everywhere, so therefore the Cauchy-Riemann equations hold everywhere. Yep.
That's the same as being entire.
Entire, yeah, the word for holomorphic everywhere is entire.
Professor?
Yes?
If the different components are C1, like everywhere, but the Cauchy-Euler equations don't hold on don't hold on all of S, but only hold on part of S, what would that mean that you get there?
Yeah, I mean, that's not going to happen generally. I mean, the fact is, like, yeah, I mean, basically what you can do is if these don't hold everywhere, like, you figure out where they do hold, and then that's where that's where the function is analytic. In fact, it will correspond exactly.
Okay.
That's a good question. Okay, so another classic example is to deal with functions like this one, right? Why don't we include functions that have z bar inside of them? F of z is equal to z bar. Let's see what happens when we feed that thing in to the Cauchy-Riemann equations, because I suspect this is going to go to what you're asking. This is going to have nice partial derivatives, right? Because f of z is equal to z bar is the function x plus iy bar, which is x minus iy. Those are perfectly nice functions, right? The real part is u, and the imaginary part is minus y, or sorry, the real part is x, and the imaginary part is minus y. So here, u of x and y is x, and v of x and y is minus y. Certainly those are smooth functions, right? They're just polynomials again, they're smooth. So these are C1. So it's possible the Cauchy-Riemann equations can apply. So let's see if it's ever the case that ux is ux equal to vy. Well, let's see. Ux is 1, and vy is minus 1, and that's never true for any value of x and y. And so that's a proof that z bar is analytic nowhere. Sorry, holomorphic nowhere. There's nowhere that that function is complex differentiable. So the conclusion is, thus, the Cauchy-Riemann equations are satisfied nowhere. Nowhere. So f of z is equal to z bar is holomorphic nowhere. And why would you deal, so again, the field of regular complex analysis is only of holomorphic and analytic functions. And that means generally the reason we don't see z bars running around in our functions is because of this behavior. The z bar showing up, or a bar showing up inside of a function is going to negate something which is going to screw up the sign of the Cauchy-Riemann equations. And that's why we don't ever have, like in all the stuff we've done in here, we've done very little where functions involving z bar are used in any sense. Okay? All right so far? Okay. Man, I get to do all kinds of, there's all kinds of fun examples to do here. But let's actually see if we can figure out why the Cauchy-Riemann equations might be true. So Here's a one. It's this pile right here. Okay, so let's assume, so what we're going to show, I'm going to try to convince you that these, like, why these things are true. So we're going to prove this direction. We're going to prove that if f is complex differentiable on a disk, then ux is equal to vy and uy is equal to minus vx. So we're going to do that direction. So complex differentiability combined with the decomposition of the function into real and imaginary parts is going to force this to be true. All right. So if this is even going to have a chance of being true, let's just assume all the pieces we need are C1. Because if they're not C1, then it can't be complex differentiable. So we're going to assume that ux, uy, vx, and vy are continuous. So they exist and they're continuous. Everywhere we're interested in, all the first partial derivatives and the main functions themselves, I forgot v, u, v, ux, uy, vx, vy are continuous functions. Okay, so if I have that, somebody remind me, what does it mean to say that f is complex analytic? Assume f is complex. Sorry, not analytic, differentiable. Differentiable at, say, some point z in the disk S. What does it mean to say that? Complex differentiable means what? Definition of complex differentiable.
Difference quotient limit exists.
F prime of z is equal to the limit as z goes to, h goes to 0 of f of z plus h minus f of z over h. Okay, so if I'm differentiable at a disk, what I'm going to imagine is that all the points around z are legal to plug into this function. So I'm going to cheat. This is a, what if h was a real number? I mean, after all, that difference quotient holds for any h tending to 0, right? Any h tending to 0 is going to make this, is going to agree with this limit. So if I want to, I can pick specific directions to approach 0 from, and the equation will still hold, right? Doesn't matter how I approach 0, every possible direction I choose, the limit's going to be the same, and it's all going to be f prime of z. So I'm just going to pick a direction, which is h is a real number. So that means that the limit as h goes to 0 of f of z plus h minus f of z divided by h is equal to the limit as h goes to 0 of f of x plus iy plus h minus f of x plus iy divided by h. I haven't done anything yet. I just replaced z with x plus iy. But if h is real, then that means I can lump it in with the x, right? So this is equal to the limit as h goes to 0 of f of x plus h plus iy minus f of x plus iy over h. Yeah, h is assumed to be a real number, so I'm going to stick it together with the x up there. And then I'm going to take this, and I'm going to break it into real imaginary parts. So I'm going to get that this is equal to the limit as h goes to 0. I might be overdoing the notation here, but u of x plus hy plus iv of x plus hy minus u of xy minus I times v of xy all divided by h. I mean, I haven't really done much here, right? Again, all I've done is I sorted the h in with the x. I've replaced f with its real and imaginary parts. Now I'm going to sort that into two different difference quotients. It should be pretty obvious what's happening here, if you've seen this type of argument before. So this is u of x plus h y minus u of xy divided by h plus I times v of x plus hy minus v of xy divided by h. We made the assumption that u and v were differentiable functions, right? All with nice continuous partial or like partial derivatives. So what's this? Partial derivative of u with respect to x. It's the definition of the partial derivative of u with respect to x. So this is ux. What's that? Well, it's the partial derivative of v with respect to x. This is how these partial derivatives work, right? Plus I times vx. Okay. Well, that doesn't seem very exciting. I took the derivative of f, and it turns out to be the case that the derivative of f restricted to this direction turns out to be ux plus ivx. But remember, this limit is the same no matter which direction I came in from. So this really is f prime of z. Right? The only thing I did here was I said for this specific direction, every direction you come in from, the limit here is f prime. Every direction. In this specific direction, we end up with this formula for f prime of z, but it's still f prime of z. Now, if you run the same calculation, which I won't do because it's exactly the same, but instead you start with the difference quotient where you take the limit as ih goes to 0 of f of z plus h minus f of z over h over ih. So now you make it a purely imaginary part. It's like now what we're going to do is we're going to do the same limit, but we're going to come in along the imaginary axis instead of the real axis. And you grind through the same algebra. Again, you're going to end up with a difference quotient, but now what's going to happen is there's going to be things in the y variable instead. There'll be a y plus h over here. Then what happens is you end up, you grind this. This is f prime of z still, but this turns out to be equal to vy x and y minus I times uy of x and y. So if you come in on now this step right here, I would suggest that you do that calculation. Do the algebra on that calculation and make sure you understand how to build that, how to take the difference quotient and pull it down, because I might ask you this. This argument is straightforward enough, I might ask it of you. So practice this to show that this formula is true. Practice this, which means don't cheat and look in the book where he does it in full detail. Try it. So what's the point of having done this twice from two different directions? So we've got these two different formulas, and both of them are equal to f prime of z, and are derivatives unique? Yes. Well, sure, last time I checked they were, right? You can't have two different values for a derivative. So on the one hand, this is equal to ux plus I vx. But on the other hand, this turns out to be equal to vy minus I uy. And if you have a complex number, and you have two different presentations of the same number, then the real parts must agree and the imaginary parts must agree. And so from here, because the real part, this is just a number. If you have a complex number, the real parts of two different presentations must be the same. And the imaginary parts of two different presentations must be the same. So you're just basically, it feels kind of cheesy, but it's a trick, right? We're just using directional derivatives to pick up different formulas that must be equal. And so yeah, you could get different formulas if you chose different directions, but then you'd have even more directions than you need for the Cauchy-Riemann equation. So why not just go with the coordinate directions? It's the usual argument there. All right. Questions about this? Any questions? I have a question. Which is, where did this come from originally? Like, where does this originally come from? Does anybody actually know where this comes from? Have seen it before?
I have no idea, but my intuition says something has to do with conservative functions and group theory.
Okay, so the conservative function stuff, that we're really going to hit that when we get up into, so yes, actually, secretly every complex analytic function can be thought of as a conservative vector field, but we'll come back to that. But that's the reason why all this structure works, is that really secretly complex analysis is the study of conservative vector fields in a different language. The original motivation for this comes from something called Laplace's equation. Okay, so Laplace's equation says this, which you can think of as being fxx plus fyy is equal to 0. Right? So this is called Laplace's equation. And historically, Laplace's equation shows up in the study of the distribution of heat and electromagnetism. So it's like it's one of the fundamental physical equations. And solutions to Laplace's equation, so I mean, this is a differential equation, right? I don't know if this has a solution, but if something is a solution to this equation, if you can find me a function that satisfies this, it's called a harmonic function. Solutions to this differential equation if you've taken partial differential equations, you've probably seen this before. Solutions to this differential equation are called harmonic functions. So let's look at something real quick here. So I'm going to write down an analytic function, and then we're going to investigate the pieces of that function. So let's take a look at I was going to do e to the z, but I sort of changed my mind here. Let's take a look at this. Let's take a look at f of z is equal to z to the third. Now, hopefully you guys agree with me that that's harmonic everywhere. Right? I mean, it's, or not harmonic, sorry, holomorphic everywhere. Holomorphic everywhere, yeah? Okay, and that means that we know that it's going to satisfy the Cauchy-Riemann equations. But let's take a look at its real and imaginary parts. So if I take this function and I write it as f of x plus iy is equal to x plus iy to the third, and I sort of boil that out, let's see if I can do this right. Why am I doing this to myself? X squared plus 2ixy minus y squared times x plus iy. It's the i's are killing me. All right, just be using the Pascal's triangle here. X to the third plus 2ix squared y minus 2xy squared. This is what you have to look forward to in your homework. X squared y. Doesn't it look amazing? Oh shit! I fucked this up. Hold on. All right, x. You guys gotta double check me here. X to the third and 2i. Yeah, but the i's like flip the signs, right? Forget it. I'll just deal with the powers. It's x to the third and x squared, 3x squared y, and 3xy squared. See, even though the y's, see here, there's Jack. Okay, so I'm going to ignore the I for a second. I'm going to write x to the third plus, oh, that doesn't work either.
It's x cubed minus 3xy squared.
X cubed minus
plus 3x squared y minus y cubed, and the last two terms are all times I.
Hold. Okay, so it works like the way I think I.
Yeah, y splitting had it right. Okay, x cubed minus 3y squared x plus 3x squared y minus y cubed, and then that whole second two terms are all times I.
Right.
Yeah.
Okay.
It was the 151.
Yeah, it was. I got myself turned. I got myself turned around.
That's a nightmare.
Okay. So, we call this function u. So u of xy is equal to x to the third minus 3y squared x. What's ux? Good practice. 3x squared minus 3y squared. So the x derivative, right? So only the x gets differentiated. And what's uxx? 6x. And what's uy? Minus 6yx. And uyy is minus 6x. So the real part of this function satisfies Laplace's equation. Uxx plus uyy is equal to 0. Uxx plus uyy is equal to 6x plus negative 6x, which is 0. And so the real part of f is harmonic. And also, if you go through it, the imaginary part of f is harmonic. And that means f is harmonic, right? I mean, f's not harmonic, it's not real value, but it satisfies the same sort of structure. So the idea is, like with harmonic functions, yeah, f isn't harmonic, but its real and imaginary parts are. And this is not an accident. Analytic functions, which are, again, this is related to the conservative vector field observation, right? Analytic functions come from motivations in real physics in two variables. So the study of harmonic functions is really secretly the study of complex analytic functions, right? Harmonic analysis isn't the same as complex analysis, but the ideas of harmonic analysis, the study of harmonic functions, lead to ideas in analysis. And even better, if you identify a harmonic function, so suppose that somebody came along and they didn't tell you this. They didn't tell you f of z was equal to z to the third. They just told you you've got a harmonic function. Hey, I've got this function u of x and y that's equal to, whatever it's equal to, x to the third minus 3y squared x. And it's harmonic. It turns out that up to a constant, you can recover this just with a computation. You guys remember, I mean, how many of you guys took, it was exact equations in differential equations? You would have done this annoying thing where you integrated, you had this integrating factor, and you knew if you integrated one way that the partial derivative destroyed the extra function in x, so you had to integrate it, and you got a constant. It wasn't a constant, but it was a constant of the other variable, and then you had to integrate back down again to find it. That same technique, basically, can be used to recover whatever the imaginary part of this analytic function is. So really, when I say that these things are like the study of conservative vector fields and exact equations, I literally mean it. It's like I'm giving you the m from an exact equation, and you can integrate back to figure out the n that went with it. And the f, the potential function, is what you think of as being the analytic function that sits over it all. Yep.
Does being a harmonic equation imply that you will have you'll be holomorphic in the complex?
It doesn't. No. So like, oh, you mean like if you have this equation?
Yeah.
If so, the question is does this function being harmonic imply that you satisfy the Cauchy-Riemann equations? And the answer, I believe, is
In either direction.
no, I'm not actually sure. You use the harmonic conjugate. You use the Cauchy-Riemann equations to build the harmonic conjugate. So no, I mean I think the idea here is you start with something that's harmonic. The fact that it's harmonic gives you a method to get back and forth. I mean the fact that this exists is going to basically get you Clairaut's theorem, and then you go backwards to find the function that they came from. So Yeah, what you should think here is the harmonic function comes with something called a harmonic conjugate. We don't have time to do it today, but I just want to introduce the idea of harmonic functions and their connection with the analytic functions. Okay? So that's a good question, and we will come back to it. But before we finish today, let's finish up our terminology here, which is harmonic functions are solutions to this physically motivated problem. The pieces of an analytic function are harmonic, and if you give me a harmonic function, say this, I can find the harmonic conjugate of u, which is v, and then f is equal to u plus iv is analytic. So the idea is basically, once you have u, you can use the Cauchy-Riemann equations to force what the structure of v has to be to make this analytic. And it's better than that because the harmonic conjugate is essentially unique. You guys remember when you did these solutions? Maybe you don't remember, but when you do the solutions of these sort of differential equations, you always get this additive constant, the plus c. Up to that plus c and this process being the same, you sort of do this partial integration, which I'll show you next time. The v that you get is unique up to that constant. So analytic functions reduce to harmonic functions, and harmonic functions can be expanded into analytic functions. And so this is actually one of the places where you can see why complex function theory is used in physical applications. Because complex functions can be used to study solutions to this differential equation. Okay, what's anything else I wanted to say about this today before I let you guys go? Right, so what I want you to practice if you get the chance is kind of what I did right here, badly, I'll say. Which is why you should never try to cook up computations on the board. You should practice a couple of these, right? So some of the exercises that I've given you on the homework are precisely this, which is I give you an analytic function sorted to its real and imaginary parts and go through the process of showing that those real and imaginary parts satisfy the Cauchy-Riemann equations, and then also showing that the pieces are harmonic. And then next time what we'll talk about is how you start with a harmonic function and recover its harmonic conjugate to get an analytic function. And that's the real bridge between the physical engineering applications of complex analysis and the sort of pure complex analytic mindset. All right, see you guys next time.